All right, so in number 10, we're still doing the operations of sets, but we're not looking at a list of elements like in number 9. We're looking at interval, and as we know, the interval of numbers includes infinite many numbers. So set A, as shown in the on the number line, it includes numbers, all the real numbers from -1 to 4 to 2, and because it does not x is not equal to -1, we use an open circle, and x is equal to 2, we use a closed circle. Similarly for B, it goes from 1 to 4, and x equals 1, we use closed, and x not equal to 4, we use open circle. And by the definition of intersection, we're supposed to find numbers in both sets, as we can see. So those numbers from -1 to 2 are in A, and those numbers from 1 to 4 are in B. As from the graph, we can see that numbers from 1 to 2 are in both A and B. So that's why we have this answer. And make sure you put an equal sign for 1 and 2, because 1 is in A and 2 is also 1 is both in A and B, and 2 is also both in A and B. So both 1 and 2 should also be included in the intersection. And the complement definition is anything not in A. So from the picture we can see from -1 to 2, not in A, that would be less than -1 or greater than 2. So any number not between -1 and 2. And again, -1 is not in A, which means it has to be in the complement, because that's the definition of a complement. Not in A, and then it's in a complement. But 2 is in A, that makes 2 not in the complement. So that's why we don't have equal sign for 2, but we do have equal sign for -1. Now, when we do the union, it means either or. As we know that from -1 to 2, that's the numbers in A, and 4 to 5, that these are numbers in C. And by the definition of union, it's either here or there. So we have, because there are two separate parts, we cannot really put them in one interval. So we got used two separate inequalities. The last one, the complement of A intersection with B. So we can use the answer from part 1 to take the complements. So anything less than -1, and anything greater than 2, because 1 and 2 are both in the intersection. That makes them not in the complement. So that's why we cannot include 1 or 2 in the complement. Again, because the numbers between 1 and 2, including 1 and 2, are in the intersection. They will, anything not between 1 and 2 will be in the complement. And number 11, so we can see that there are two parts of the this question has two parts. So first we found the Cartesian product of A and B. By the definition, it's like forming points. So the x-coordinate comes from A, the y-coordinates comes from B, and A only has one element. That's why we have A in the as the first component. But the second component comes from B, and B has two elements, so we could put 1 here or 2 there. So when we do that, it's pretty much you start with the elements from A, and you do like distribute, kind of like a distribution. So we do A1 as 1 point, A2 as 1 point. And we can always think of the elements of Cartesian product as a point, so that it has 2 points or 2 elements in the product set. In the second part, we got to do the power set. The power set means all the subsets of the product set. In this case, well, because the original set has 2 points, so we can form either a set with no elements, which is empty set, or we can for a set with only one point, which is A1 or A2. So there are two possibilities with only one point. There's another possibility to include two points in there, which is the original set. So these are all the possible combinations of all the possible subsets we have. And in the last problem, number 12, we must use the element argument to prove this statement, to A union B is equal to B. So as I break down here, step 1 and step 2. How do we prove two sets are equal when they are subsets of each other? So there will be two cases that we have to prove. Two steps. A union B is a subset of B, or B is and B is a subset of A union B. So in step 1, how do we prove a set is a subset of the other? By the definition, we need to prove every element of A union B is also an element of B. So let's use X to represent a member or element of A union B. So let X be an element of A union B. Well, by the definition of A union B, it means X is either in A or X is in B. So there are two cases that we have to do. So case 1, X is in A. Case 2, X is in B. If X is in A, our final goal is to show X is in B. And because in the condition we know A is a subset of B. By the definition of subsets, any element of A is also element of B. Well, because X is an element of B, A, that makes X an element of B, because A is contained in B, the subset definition. And so we proved that if X is in A, then X is also in B. In case 2, X is in B, which there's nothing to prove. X is already in B. So in either case, we can prove X is an element of B. Now look at the beginning and the end, the first statement and last statement. X is an element of A union B. X is also element of B, which is exactly the definition of subset. Every element of A union B is also element of B. Now in step 2, this time we want to prove B is a subset of A union B. So we're going to pick an element from B. Let X be an element of B. Well, the definition of X of A union, over here we have actually we don't have to do two cases here, because if X is in B, then X must be A union B. There's not really necessary to do the two cases. So for step 2, it's much easier. So all we have to do, step 2, in step 2, we want to prove B is a subset of A union B. In step 1, we didn't have to do two cases because we don't know where X is from. X could be in A or could be in B. But in step 2, because when we pick this X comes from B, we already know for sure X is from B. And well, if X is in B, then X is in A union B. Immediately, this follows from the definition of union. Then X is in A union B, because the definition of union says if X is in one of them, doesn't matter if it's in A or in B, then X has to be in the union. Well, we know for sure X is in B, then X is going to be in the union. So that's all we have to write down for step 2.